Hey guys, probably one of the last presentations, jet lag hitting us, so I'm bound to fall asleep. So just wake me up with questions. I love the questions, so we don't have to wait till the end. So if you see myself nod, usually I talk very fast. So if you see myself slow down a little bit, just kind of give me a nudge and stand up and ask me questions so we can keep this going. So just a really quick intro about myself. CTO for Mu Dynamics is a company that I started some years ago, and we got acquired in April, and now I'm CTO for Blitz, so Blitz kind of lives on. I've been a Rubyist since about 2006. A lot of people actually get introduced to Ruby through Rails. Mine was exactly the opposite, so we actually built 250,000 line of code commercial non-web app application in Ruby, and I'll go through a little bit about what we did and why performance was pretty important for us. So Mu Dynamics, when I started, anybody know what fuzzing is? All right, so I'll go through just one slide. All right, so it was essentially we built a commercial fuzzer on steroids, and before I talk about what fuzzing is, our very first version was in C++. Yuck, you say, right? So it was pretty hard to maintain, and so when we started moving some of the stuff over to Ruby and trying to put some Ruby, lipstick on the C++ pig, and kind of struggled through it a little bit. And then the third version, we pretty much switched almost completely to Ruby, and then we had to do a bunch of stuff with C extensions to kind of optimize that. So for those of you that don't know what fuzzing is, anybody familiar with this one? It was a GitHub Rails vulnerability. It's not meant to be a put down on GitHub. I love GitHub. We actually use GitHub for Blitz. But essentially, it was a SQL injection vulnerability. So you could essentially take over and do mass assignment with Rails and take over other people's SSH keys and all of that fun stuff, right? So that's kind of what we did. We essentially did something called hacker-driven development, which, if you have a RESTful API, maybe you're using Rack or whatever else it is, we could take your RESTful API and very methodically generate tons and tons of automatic unit tests that essentially are all triggered around either crashing the Ruby app, generating as many exceptions as we possibly can, input tampering, things actually missing, things that are overflowing, things that look like email that are not supposed to be like email. So we would just automatically generate all these thousands of test cases. And so the whole idea was you kind of incorporate security testing and vulnerability testing into your development process instead of running an audit once a year. So that's kind of the company that I built. And so because we were generating these tens of thousands of test cases, these things tend to run for 3-4 hours because it was very exhaustive and methodical, right? So we wanted, and we love Ruby, and I'll tell you why in a second. And so we wanted to make this thing go faster because we couldn't wait around for 36 hours for 1,000 test cases to run. So we did a lot of stuff in order to break pretty much everything. It was a lot of fun. We broke printers. It didn't matter what protocol that spoke. We broke printers, little fans in Mines that it's called SCADA. If you're familiar with that space, Rails application, Python. It didn't matter. We broke everything and found a lot of problems with it. That's kind of the product that we sold. So the speed of execution was actually super important for us. Okay. Anybody still think I'm yawning or slowing down? Okay. Cool. So we love Ruby because after going to C and C++ and all of that stuff, right? So it was very clean and beautiful. We love that as a language, but also it was beautiful both on the outside as well as the inside. So when you write C inside of Ruby, it actually felt like you're writing Ruby. So a lot of the methods that you're using internally were very similar to how you would use it outside, okay? And so extensions, as we talked about, is almost like writing Ruby. And so 192 is a little bit more complex because of the whole virtual machine infrastructure that it's there, but 197 is almost pure, okay? So since this is a talk about performance, and performance is this huge subject, right? You can kind of pick up any one of these pieces and you can talk about it all day long. So just a quick note on languages, right? I mean, people say Node.js is fast, or Rails is slow, or Python is okay. And I mean, languages by themselves are just abstract. It's like saying English is faster than German, or something like that, right? It just doesn't make sense. So, but when it comes to programming languages, the interpreter has a lot of trade-offs it makes, whether it's method caching or caching all the regular expressions or things like that. That matters a lot. And so you kind of have to know a little bit about optimization and gotchas. And actually, throughout the day, there was a lot of really great presentations on performance. And actually, Aaron opened up the keynote with just talking about Rails 4 and threading and concurrency, which I will touch upon a little bit more. But in my mind, just after working with Ruby and all of this stuff for many number of years, I think it actually comes down to big O. Anybody know what big O is? All right, cool. So big O, you've probably seen this, in computer science classes. They talk about O1, order of log n, order of n squared, etc. But essentially, it tells you what the speed of execution is, or how much memory something is going to take. It's in a very abstract way of describing it. Okay? I mean, a lot of times when you encounter a performance problem, it's one of those things that makes you go, duh, and then you kind of dig deep into it. It's usually an order of, problem with the either choice of poor data structures, or it's the wrong choice of algorithms, and a lot of times you're capped by speed of light too, which means latency, right? You just can't push things fast enough. If your data center is in Germany and all your customers in US, you just can't push packets fast enough across the globe. So you're kind of limited by the speed of light. And most people would say, Rails are slow. It's like, don't, So you usually dig deep in it, you find out that it's really the way you're using it. I think just the last two presentations ago, I think Ben, I think it was Ben. He had this date range dot includes. I don't know if everybody paid attention, right? Includes versus cover. So big difference, right? So date range dot includes essentially expands Ruby to go through every single element and does a comparison check. So that's order of n. That means if you've got 300 years in it, it's going to go through every second of every day of every year to scan through the whole thing. Versus cover with the question mark, that method essentially checks the outer bound, the inner bound, and the outer bound, and that's O of 1 regardless of the size of the date range. So the complexity, order of complexity, is a pretty cool metric of tracking down whether your stuff is going slow or fast, etc. Okay. So in terms of if you want to plot the complexity, it's a pretty nice way to actually look at it. So the yellow line is order of 1. It essentially means that, so the bottom line is the data set size, right? So it could be millions of entries in a database, or you're holding thousands of entries in Redis. Maybe your active record SQL query essentially gave you back 10,000 elements. So really the order of 1 tells you that regardless of the data size, the time to access a particular element is the same, okay, in terms of data structures. So log n essentially is pretty nice. That's the little blue line at the bottom. It basically says, it kind of grows in a logarithmic way. That means you can have 1 million entries in there, so it's still not going to be as super slow, and that's a good thing. Purple line, you're starting to get into the worst situations now. Purple line is the more the number of entries, the linear the performance degradation. Okay, if you've got 1,000 entries, your algorithm runs fast, reasonably okay. When it gets to 1 million, it slows down by that order, and that's terrible. And the ON squared, you don't even want to go there. That's the nightmare of all, right? So you want to make sure that you don't go there, because very, very quickly things get completely out of whack, and your entire program just comes crashing down. Things get really slow and sluggish. And so the way I'm going to talk about performance is, instead of kind of talking about very abstract in a way, so I'm going to use some of the product that I'm working on as a way to actually convey some of the concepts like concurrency and threading and hit rate and stuff like that you've heard throughout the day. So hopefully it's a slightly different way of presenting it, but I find that thinking about abstractly, it's really hard for me. So if I can use specific concrete examples, then it's much better. All right, so we'll start with very little things, okay? So this was just a really simple example of the power of the big O notation. So a while back, I did this gem install T. I saw this on Twitter. Somebody actually had a Twitter client. It was very cool. So I just did gem install T, and I just typed T, enter. And it was 1.34 seconds before I got a prompt displaying the usage of this program. I'm like, that's wrong. I mean, 1.37 seconds for a program to just display usage, that doesn't sound right. Okay, so let's dig a little bit deeper. So you load up bin T, and then you find that in line 4, I basically said, just print out the loaded feature size, which is the number of files you've required inside Ruby. That thing keeps track of it. Okay, and then exit 1, so you run it again, now it's 433. So really the number of dependencies that this program had was 433 other files that it was requiring. Okay? That's still not, if you think about it, right? It's just an array, it's 433 elements, and you should be able to scan that pretty quickly to, really not a big deal. We're not talking about 1 million Ruby files that you're including or requiring. So now you find out what the class of this loaded feature thing is. Turns out it was an array. Okay, so now red flags start going on, right? So what's actually happening is, so inside the load.c, inside the interpreter, so if you look at what actually happens when you do a require Ruby file, whether it's a Ruby gems or whatever else it is, so say require active record. So there's this little loop here. For those of you that don't understand C, that's all right. It's a pretty simple loop that basically says I equals 0, I is then less than the array length, okay, of all the files that you've included. And then for each one of them, it basically goes in there and compares, whatever you're loading against all the elements that have already loaded. Okay? Now, who knows which big O that falls under? Okay? So let's simulate to find out what the graph looks like, all right? So I just randomly started adding stuff into loaded features, and I just kept calling require over and over again in a little test harness. So the graph looks like this, which is what? Come on, you guys. I'm falling asleep, not you. All right, n squared, all right? So it's n squared because for every require, you're scanning all the other things that have already been required. So every new element touches all the other element over and over and over and over again. So how does this affect in real world, you know? So gem install Rails, create a new app, load config routes.rb, and print that loaded feature size is 784. So out of the blue, a Rails app has 784 dependencies, okay? So really, the point of this exercise is performance is everything from small to everything from big. You kind of have to worry about, or at least think about what the big O is. So this manifests itself in the startup time of Rails. That's really what it is. I think in the last presentation, we were talking about how JRuby takes forever to load the first time. It's doing a cold start. It's loading everything possible and compiling and JIT and all of that stuff, right? So that essentially manifests itself in load time. So as you start just using lots of these gems and just requiring everything else, it's kind of like the same as Chrome's page speed. You know, if you can look at it, it basically tells you don't use this CSS rule is never used in any other pages. You might want to prune it, kind of stuff. It's the same thing. Kind of watch your dependencies. So if you're not using any particular gem, it's better to prune it because that's going to improve your load startup time. All right, so far so good. Medium things. I'm a huge fan of Feynman, so you can kind of see where this is going. Very quick intro about Blitz here. It's not meant to be a huge plug, but how many of you know what Blitz is? Cool. So when I built Blitz, it's a distributed app for load testing. That's what we do. So very, very high level. I'll put this on SlideShare so you can take a look at it. Very, very high level. You can basically say, look, I've got this Rails app on Heroku, Nginx, PaaS, whatever, on your own EC2. And you can say, send me 10,000 virtual users from Singapore. And we basically tell you, here's kind of what the response time looked like, here's the hit rate looks like, and then we also can overlay New Relic and CopperEgg metrics on top of it, so you can find out when there are 10,000 users on my website, here's kind of what my database performance looks like. That's what we do. That's what I work on. That's the product that I work on. Okay. So here's a really simple graph that kind of demonstrates what's going on. This is New Relic data, and so the gray line, the little step ladder, is the number of concurrent users that we're sending against your app. You can see the response time graphs in yellow, and the blue line is basically the CPU usage that New Relic is reporting, all overlaid on top. Okay, so it's a pretty simple app, but it's a pretty powerful way to constantly incorporate performance, measure the performance of your app on an ongoing basis. End of plug. Okay, so let me just talk about Blitz experience, what we went through in terms of performance, right? So you figured that as a performance testing product, we're going to be immune from all of this stuff too. Wrong answer. So we're going to have to went through a bunch of different lessons along the way as we built this product. So the very first one, we used CouchDB. So there was no Redis yet. And so pretty much every request would go against CouchDB, and the front end is actually just a Sinatra app because we didn't want to, for whatever reason, we're using CouchDB and we didn't want to be burdened by the ORM mapping, so we went with Sinatra. And so the very first one, we had a before filter. Question? Almost. So the before filter looked pretty much like this. It basically says CouchDB get go in session ID, right? We forgot one thing, that all the static assets were also being loaded as part of the page load. So CouchDB was just getting hammered with like just thousands of requests, right? Because every CSS would go through this before filter. So again, this was a simple example of ON, where in the given page, if you have n number of assets, that was translated into n number of requests back to CouchDB. And so that was one of those duh moments, right? So again, comes back to big O. Moving on a little bit. So the first architecture, so the way we set up the Blitz was there was a Sinatra layer, and then there was CouchDB, and then there was all these regional, what we call engines. These are the little traffic generation engines that are sitting in all AWS regions, and they would all do something called changes feed on CouchDB, which is a way for the CouchDB to tell you that there's a new document or it's been modified, right? This is a classic case of self-distributed denial of service. So what was happening was when you say, hey, I want 10,000 users from Singapore against my website, so let's say there's 20 engines in Singapore, they would all be waiting on the changes feed. And all of them would wake up and they would go and try and write that document inside CouchDB. So every front-end web request was actually getting translated into 20 or 40 or 60 different HTTP requests back to CouchDB. So this was like a massive distributed denial of service against our own system every time we did this. So we thought it was all cool, right? Oh, changes feed, it's got to be cool. But turns out it sucked. So we had to go back and figure out how to fix it. And so the fix was essentially switch to Redis. Okay? So we now use Redis for all the queuing. Everything is in memory until there's a delayed worker, actually a rescue job that eventually takes the tests that are actually done and then moves them to CouchDB for persistence. And we didn't use rescue for test scheduling for a number of reasons. First one was back when we first started using, we actually have multiple workers per EC2 instance, and it kind of varies dynamically. With rescue, you kind of have to statically declare that you want X number of workers per physical machine. So we wanted that elasticity. And the second one was maybe because Redis didn't have it, we used this command in Redis called, it's kind of arcane, but it's blocking right pop left push. Okay, it's almost like long polling. That's really what it is. So every engine that we have would connect up to Redis and kind of wait for 5 seconds and wait to see when there's a new job or not. And if it's not, it will come back again and try to connect. So rescue at that time was actually doing every 5-second polling, which is not as efficient. So we kind of built our own at that time. I'll talk about Redis and how that plays into Big O a little bit later. And so this turned out to be amazing for us because it dropped the UI response time from about 750 milliseconds to less than 20 milliseconds. So that was a pretty huge performance benefit for us by moving to Redis. Question? Come on, guys. Somebody. Ask me what my name is. Anybody? Jet lag. So all right, so bigger things. So this one things got getting a little bit interesting. So the JRuby presentation right before me, they were talking about GC hiccups. So I figured I'll kind of show you actually what a GC hiccup looks like. So I've got this little project on GitHub. It's called Vroom, and it's deployed on Heroku. And I've got 2 routes /GC, which essentially what I did was, if you look at the source code, I disabled garbage collection. And then every time there's a new request coming to the /GC route, every 10 seconds later, it basically manually runs a full GC, just to kind of exaggerate and kind of show you what's going on. Okay, so let's see what this looks like. So I'm using Blitz. Make sure that the Heroku app is actually up and running, because they idle the dynos after a while. So here's kind of what we're going to do. So I'm going to start looking at the GC count, which basically uses object space, has a method called count objects, which essentially categorizes the object type and number of objects that are inside Ruby interpreter. So this is just kind of showing you what the total number of objects are and the different types of objects. Okay, this is a simple hack for just doing a meta tag and refreshing. Okay, so nothing crazy here. And so here what we're going to do is we're going to go from 1 to 100 concurrent users in 60 seconds. Okay, and we're going to hit that route, which is, as you can see, is /GC. And let's see what happens. Okay, so what you're seeing here is basically you're seeing the response time, and at the bottom you're seeing sort of the hit rate, how many per second. I'll clarify what these 2 things are. And you're starting to see some timeouts. And if you look at this, we went from 100 objects in memory to about 500,000 objects. And when the GC actually kicks in, that's going to drop a little bit, and then it's going to kick back again. Okay? So these little hiccups that you see here is essentially that's when the GC is actively running. So when the GC is running, because it's a single VM, GC is running on the same thread process as the primary Sinatra rack application. Everything basically comes to a stop. While GC is all the garbage collection happens. Once the Ruby interpreter gets a breather, then everything comes back alive again. See that big hiccup right there? That's basically what I'm talking about. Okay. And so if you look at this object again, you can kind of see that it's going up and down. So why does this matter? Let me see. Okay. So why does it matter? Because this was actually captured from one of our customers running a Rails app. They were just, I think they had an N+1 query issue or something like that, and using Active Record, and they were just loading objects like there's no tomorrow. So once you start hitting the app in a big way, everything would just go, just stop, and huge spikes in response time while garbage collector is busy just doing stuff, what it's doing, and then it would come back up. So object creation, it doesn't matter what programming language you use. Object creation, the less number of objects you have, it's a better thing. Just less things to worry about, and that's probably 01. Because you're going to have to touch every single object during the update cycle to figure out which ones to reap. So GC hiccups are a real problem. Okay, so questions on that one? All right, so you can kind of see that big hiccup right there, and also your hit rate taking a dive. Okay? All right. So I've talked to many people about concurrency versus hit rate, and there's always some confusion about it. So hopefully I can do a little bit of clarification on that. So hit rate, when people post it on Hacker News or whatever else it is, my website can take this many hits per month, So hit rate is basically the number of requests per second your website or app can handle, whether Rails or not, doesn't matter. Okay? And it's not the same as the average response time. And it's a pretty important distinction because a lot of time people tend to bundle those two things together. Okay? So that's hit rate. Concurrency, which kind of sort of has some implications to hit rate, and I'll show you how. It's typically when you run, when there are 1,000 users on your website, and you go to, on your EC2 instance, a line or whatever else it is, and you type list open files, -off, -n, -t, whatever. It basically shows you all the number of sockets open. That's concurrency. That's basically how many people there are at any given time on your application. It's also known as the simultaneous users. So when you define it that way, what you realize is if you use a single-threaded Sinatra application, it has a concurrency of 1. Okay? Because Ruby, there is no, you can use threads. I'm just talking about vanilla, Sinatra, no threading, no external processes, no Rails 4, no Rails 5 stuff. Just vanilla, even if you use WebRig or Thin. You've got Sinatra running. It can only handle one request in its thread on process. So effectively, it has a concurrency of 1. So let's see what it actually means. Okay, so I've got this other route called sync. Okay, you access that. You can give it a parameter called delay, which is in milliseconds. And there's basically a sleep statement. So you can see get sync. It basically has a delay. It sleeps for that many number of seconds, and then returns a value. Okay. So because it sleeps 1 second, you expect a hit rate of about 1 per second, okay, regardless of the number of users. And the average response time of 1 second. Let's try that. So let's just try a very, very simple request. And it basically comes back and says, about 1 second, there's some margin of error there. It's not exactly right? So because we're coming from Virginia, Heroku is also in Virginia, data center, latency, whatever, okay? So now let's run a really simple load test, 1-to-1. And 60. Basically, we just have one user. So the effect that we're simulating here is somebody with a browser essentially holding Apple R the whole time. Okay, so they're not letting it go. So one user goes to the website, loads the page, comes back. As soon as it finishes, goes again, comes back, goes again, comes back for about 60 seconds. Just one user. So when you try this against this app, let's see what happens. Wireless issues. Lock up. Anybody check if wireless is active? Tell us anything? I think it's just this window that locked up. All right, so let's try this again. And let's hope it works. And hung again. All right, so we'll keep going and see what happens. So typically what happens is when you do, again, one user, everything's going to be all right, right? Just one 1 second hit, 1 per second hit rate, and the average response time of 1 second, okay? So what happens if you increase concurrency? So when you typically increase concurrency, you can only fit 1 per second, and there's only one user allowed on your website. So typically when you start increasing concurrency, what the user actually ends up experiencing is timeouts and errors. That's what happens, right? So a lot of people say that, that's why WordPress caching is a big deal, or caching inside Rails is a big deal, because what you're trying to effectively do is you're trying to return the data back to the user as fast as you can, so your response time is really short, and so that you can try to accommodate as many users as possible. Okay? So one last try. If it doesn't work, I'm going to give this one up. Okay, so essentially what we're doing is I put 100 in there. If this locks up, then I'm stopping the demo. I'm not sure what's going on. Okay, so the next one is an interesting one, just a variation. So we're using asynchronous Sinatra, and which uses event machine underneath it. And so we have this route called async, which is very similar to the sync, except instead of returning the response right away, you're now telling event machine to sleep, to wake you up. It's almost like a Node.js callback is really what you're trying to do, right? Basically saying, wake me up in a second, and then return the body with that element. So this method itself, when you execute it, if you look at sort of how the method executes, this will return right away, but the HTTP connection is still pending. It's kind of waiting. And so 1 second later, event machine wakes up and invokes this callback, and then you return back to the socket that's actively open. So each request still takes 1 second, okay? But what you gain is concurrency because you're multiplexing. It's the same thing as a load balancer or a Heroku dynos or whatever terminology that you use. Is if you have a load balancer with 100 nodes in it, if each node takes about a second to respond back because it's loading this really complex page, but you still get a concurrency of 100, even though the average response time is about a second. Does that make sense? Yeah. So that's really what we're trying to do here. All right. So connection pool is another interesting one. Again, you can look at the code. It's a pretty easy. It's like a fake connection pool. I don't really have a real database there, but it kind of uses event machines to create congestion. And connection pool, the idea is, you maybe have a Postgres database with a connection pool of 50. Okay, that basically means at any given time, you have 50 connections back up to the Postgres. That's all you can handle. Now, up to 50 concurrency, you're not going to experience any problem because everything is going to be okay. There's 50 users coming in. You've got 50 connections in the connection pool. And you're going to route all the traffic through Postgres and do some complex database queries and return back. Now, once the concurrency goes up, that's when all hell breaks loose. That's basically like an 8-lane highway merging into a 1 lane. Okay, so you've got 100 concurrent users coming in. You've got a connection pool of 50. You're going to have to fit them somehow, but you can't fit them. So what happens? You got to back them up, right? So things start backing up. So what happens is, as the concurrency goes up, this happens when you get Slashdotted or when you get Hacker News or Twitter or whatever else it is. It's basically this huge flux of people coming in. Your connection pool is probably tiny, and everybody starts getting longer and longer and longer and longer, usually ending up in timeouts and all fail the hail whale. I mean, that whole thing, right? So that's what you see in terms of the connection pools. One last try on this demo. Otherwise, I'm going to throw this out. Okay, so it's going now. So in the case of connection pool, you actually start seeing what's happening. So you're starting to see the timeouts. Okay, because as we ramp up the user, the connection pool size, as I mentioned, it's kind of it's mocked. But the connection pool is about a size of 10, and that's all failed, all hail the fail whale. Nothing is going through because everybody's timing out. We're just trying to jam as much as we can, and we can't do anything about it. So it's a pretty interesting way of actually looking at the connection pool problem. Now the challenge is this. Most people, when they do a simple ping check against their site and claim like, 200 millisecond response time, this is amazing, my site is just super hot. Wait till the concurrency starts increasing past the pool size. That's when this manifests itself. So at very low pings, you're never going to see this problem. But once the number of users starts creeping up, that's when you see this huge problem. Okay? All right, so like I said, we use Redis quite a bit in Blitz, and for a number of things. We use for registration. So every time we autoscale the total number of agents in the system, they basically come and register with Redis. So it's almost like an IRC channel where these things come and go. We use it as a write-through cache. We use it for job scheduling, for actually the test scheduling. We also use Rescue for things like sending emails and whatever else it is, for API throttling. But here's the key thing. Redis, it's actually a distributed dictionary with a beautiful protocol built on top of it. Okay? It's the ultimate manifestation of Big O. And if you go to redis.io and you look at all the different commands and what it can do, you'll see Big O everywhere. And that's for a reason, right? Because if you have a data structure like a linked list or an array or a hash table or sets or sorted sets, they're all just ultimately book examples of different data structures implemented, except Redis does it in memory over a network. End of the day, it's no different from using Ruby hashes, etc. It's just you now have a server that's keeping all the data with it. So the thing that you got to watch out for is lists. If you have a list of things in Redis, so finding the index of a particular element, or inserting an element at a certain point inside the list, or removing an element, these are all ON. So if you've got 1 million entries inside Redis as a linked list, watch out for these things. So that's going to come back and bite you, and you're going to complain, or it might say, oh, Rails are slow, which is the default way to talk about these problems anyway. So you're going to have to dig deeper a little bit, and then you find out that here's the problem. Same thing with sets. So sets by default, it's the way Redis implements is it's something called it's a form of a linked list, but they actually have an interesting implementation there. It's all log n. But when you take two sets and you try to do a difference, or you do a union, at that point it all becomes ON. Okay, so you kind of have to watch out. So that means if you're taking two sets of million entries and you're trying to do an intersection, somebody has to do the work, right? It's not all automagic. So you're gonna have to watch out for that. Same thing with sets. Some of the other operation like intersection. Intersection, that's ON times M. That means if you've got a set of n elements, you've got another set of m elements, you try to do intersection, that's order of n times m. So remember that curve, exponential curve that goes up? That's what happens. Okay. So sets, definitely you're gonna have to watch out for it. All right. So I'm kind of wrapping up because I guess I skipped over a bunch or something, or maybe I'm just slowing down too much, jet lag. So probably my last slide. Happy to take questions after that. But really, performance is really just a fun sport. Once you start digging in there, Ruby or not, it's definitely a fun sport because usually it boils down to, like I said, data structures and algorithms. So when we were doing Blitz, in the early days of Blitz, we had a customer that was running geospatial queries on their database, and you've probably seen this in production too. They had it was an iPhone sending some kind of RESTful query with the lat and long, and they were trying to look it up to create a heat map, really cool app, iPhone app. And so they had indexed the X column, they had indexed the Y column, but they had not indexed X and Y together. So now what happens is if they got 1 million entries, 1 million users, and they're trying to generate a heat map, when we ran Blitz against it, it would essentially, the database would just get pegged. CPU utilization on the middle tier, the web server, peachy. It's all awesome, looks great, but the database was just getting hammered. So you start digging in there, and it's not like we're generating a lot of load either, right? And then we start digging into it, we found an index problem. Guess what order that is? That's a linear, right? Because now you don't have an index, nice log n queries on the X and Y column together, because X and Y were indexed separately. The database was essentially doing linear lookups, trying to find the geospatial query. So 1 million users, even one user trying to access a geospatial query, all of a sudden the database would come crashing down. So performance is definitely a lot of fun. Again, just takes a little bit of experience and kind of poking around to figure out what's going on. And bottom line is it's not always Rails. Okay. So that was the end of my conversation. My talk. So happy to take any questions if you have it. Otherwise, it's time to go hit the beach. Thank you.